We're in. Yeah. Good evening, everyone. Just to say before I start the talk that I'll be taking questions at the end, so I'll make sure I leave plenty of time. So, has anyone in the audience ever come across an error page like this before, where it says, hang on a sec, our site's experiencing more traffic than usual, but you'll be able to get back to shopping shortly? Raise your hands if you have. Right, so there's actually quite a few of you in the audience, and I did some research about this, and it turns out it's actually pretty common. Even the most reputable sites displayed this type of error page about not being able to handle the level of traffic that's hitting their application, and as a result, users are not able to access their site. Even Amazon, on Amazon Prime Day, as I'm sure you can all imagine, there was a huge spike in traffic on their site, and as a result, users were experiencing a similar error page. They couldn't access the site to make the purchase they really wanted to make. But going back to the jQuery experience, I have to be honest about it. I was slightly embarrassed, if not disappointed. When I visited this site, I was thinking about my user experience as the customer, not being able to make the purchase that I really wanted to make. But I never thought about it from the other perspective. I build websites just like the examples above, and never once did I think, could my users be having a similar experience? Hi, my name is Katie Koschland, and I'm an engineer and technical lead at the Financial Times. And today, I'm going to talk about my load testing journey. And I'll aim to cover the core concepts behind load testing. So I'll start with a challenge, and this is how I came across the topic of load testing. And then I'll go on to explain what it means to load test your application and how you can get started with writing your own scripts. I'll then go on to explain how you can use the metrics to help identify a performance issue within your application, and discuss the tools and techniques that we use at the FT to help troubleshoot and improve such performance issues. And finally, I'll conclude with some outcomes. So, the challenge. I recently finished a 3-month secondment in the Operations and Reliability Engineering team, and they were developing the BizOps API. The purpose of the BizOps API was to provide a central store for all business information at the FT. So, as you can see above, the model illustrates the type of information that would be retrieved from the BizOps API. It provides information about systems, how systems relate to each other, and how those go on to relate to teams and people across the FT. So it was really important for us to be able to understand the technical limits of our application, as it was going to be used frequently across the FT. So that was my challenge. It was about testing the technical limits of the application. But more specifically than that, could I answer the following 3 questions? Will our application crash? If so, can our application recover? And what exactly happens to the user experience once we've found our application's limit and we've pushed past it? Does the user experience degrade gracefully, or does it just cause absolute meltdown? I was told that the answers could be found by load testing my application. So, what exactly is load testing? A colleague of mine recommended an excellent talk by Jad Mauchi where he describes load testing in simple terms. It's about simulating ordinary user activity and then applying enough stress until it reaches failure. I really like this definition, but it kind of led me to my next question, which is, how can I apply this so-called stress to my application? So first, you need to decide on a testing framework. There are many testing frameworks out there, including popular ones like Apache Bench, Locust, Artillery, Work, and Gatling. But I decided to go with Artillery. And it was for the following 5 reasons. First, it could be installed using npm, which was great if you wanted to get started quickly because we were building a Node application. Next, it allowed you to customize JavaScript code within your scripts, and this was particularly helpful for the situation where we wanted to generate random write queries. So it meant you could write it as a separate function, and then every time a virtual user was to make a request, you could just call the function. And it's also helpful if you wanted to write a separate function that sets the headers or cookies. So above is an example you can see where we set the headers for each request. So all I would have to do in my script is call this function each time a virtual user was to make a request. Another advantage was that scripts could be configured using YAML. Above is a snapshot of one of the scripts I had written, and you can see by writing it in YAML, it makes the test scripts very easy to read and maintain. You can also see here that I'm calling the setHeader function that I showed previously. And it's also targeted towards continuous integration. Unfortunately, I didn't have a chance to implement this, but this is something that's particularly interesting that I would like to do in future projects. If performance is a high priority within your application, what you can do is you can configure your continuous integration, let's say Circle CI, and it can run your script each time you trigger a build. This way, you're able to detect at each point of your development process how a feature directly impacts the performance. So it allows you to detect any regressions within your application. And finally, it provides detailed metrics, and I'll go on to explain this shortly. But once you've decided on the testing framework that's suitable for your application, then you need to think about what type of requests would be hitting your application. Your test scripts need to be able to represent ordinary user activity. And the best way to think about this is to think about your common user journeys on your site and try to capture those type of requests that the user's making. This way, you can replicate the exact behavior in your script that your real users are making, and so it's a more accurate representation. And next, you need to decide on the shape of load that would be hitting the application. You're probably thinking, what do I mean by the shape of load? Take the graph above as an example. It illustrates the shape of load that was hitting the ft.com homepage during the 2017 election results. You have time across the x-axis and then the number of user requests on the y-axis. You can see here how the shape of load changes over time quite drastically. There are peaks where the number of concurrent requests per minute are very high, causing a spike in traffic. And then there are troughs where there is significantly lower level of concurrent requests per minute. So you want your scripts to test the different shapes of load that could potentially be hitting your application over a period of time. And this can be challenging. Before production, it's really difficult to predict the number of concurrent requests and how they would ramp in over time into the application. However, it was really crucial if you wanted your scripts to be as robust as possible. So if your application's already in production, you might already know the shape of load that's hitting your application. A situation where you could predict the shape of load would be before the release of a push notification. So the FT mobile app recently sent out a push notification to users about Interserve, and it was to notify them about the fact that they were about to go into administration. Before the push notification went out, the app was doing approximately 250,000 requests per minute. And shortly after the push notification was released, it reached 2,800,000 requests per minute. But it wasn't just the app, it was also the website. ft.com, before the release of the push notification, was doing 200,000 requests per minute. And shortly after the push notification, it more than doubled to 500,000 requests per minute. So in this situation, we would know the shape of load that we would want to test in our script to see if the application could handle that spike in traffic. But It's also okay if you don't know the shape of load that's hitting your application. As the BizOps API was in the development stage, it was really difficult to predict the number of concurrent users and how they would ramp in over time. However, as I mentioned before, it's really crucial if you want your script to be as robust as possible. If this is the case, you might want to consider splitting your script into 4 separate phases. This way, your script is capturing the different shapes of traffic that could potentially be hitting your application over the production cycle. Depending on the size of your application can depend on how you define those separate phases, but I will show you what I decided was appropriate for the scale of our application. So first I defined a warm-up phase, and this was the arrival rate of 10 virtual users per second that lasted for just 60 seconds. Then I defined a ramp-up phase, and this was when you went from an arrival rate of 10 to 25 new virtual users per second for 120 seconds. And then I defined a cruise phase, and this was the arrival rate of 25 virtual users per second for 1200 seconds. And finally, I defined a crash phase, and this is the concept of finding the limit and pushing past it. And this was the arrival rate of 100 virtual users per second for the short burst of 30 seconds. But it's really important to note that there's no point hitting your application with a load that you know it can handle. The purpose of this phase is to make the application crash. You want to be able to understand the exact behavior of your application once you have pushed past the limit. Once it's crashed, will your application be able to recover on its own? If not, how long does it take to recover? And will an engineer have to go in the middle of the night to fix the error? These are the type of questions you want to be able to answer from the crash phase. And to visualize the 4 phases, I've identified these 4 phases in a production cycle. Again, it's a graph showing the number of requests per second hitting the ft.com homepage over a 24-hour period. So you can see from 12:30 a.m. to 6 a.m., there's this low level of 5 requests per second, which is what I've defined as the warm-up phase. Then, from 6 a.m. to 9 a.m., there's this gradual increase in the number of requests per second. And this is clearly during our users' daily commute, and what I've defined as the ramp-up phase. And then from 9 a.m. to midday, there's this constant rate of about 11 requests per second, which is the cruise phase. And then I've extrapolated the graph to demonstrate what I think would be suitable for the crash phase for the scale of this application, which was around 40 requests per second. So now you've made decisions on the testing framework, the type of requests, and the shape of your load. You're ready to write your script. So let's discuss how you actually get started. What should the first script look like? So the script should be split into 2 separate sections. First is the config section. And what you do is you start by choosing the target of your load test, so the address of the API server under test. In our case, it was the BizOps API, but it was the staging endpoint. Our staging environment was an exact replication of our production environment, so we were able to test staging as it really was an accurate representation of production. And then you can specify any plugins you'd like to use. We use a plugin that allows us to send the output of our load test to Graphite and Grafana. Graphite is our metrics data store, and Grafana is the presentation and data visualization layer. And this helped us monitor the metrics over time, and create graphs that later on helped us with the troubleshooting. And then you can define the load phases, which is what we discussed previously about the number of concurrent virtual users and the method of how they ramped in. And finally, the processor. This is where you import any JavaScript function that can any JavaScript file that contains the functions you want to call within your script. So above is a snapshot of essentially what your config section should look like. And then next, you have the scenario section. This is where you identify the virtual user's behavior that it's going to be during the test. So you define the type of request that the user is going to make. You start with naming the virtual user request. In this case, the user request was going to retrieve a list of all systems at the FT and their corresponding properties. By adding a name and providing a description, you can quickly identify in the load test how frequently it was called, and it breaks down the queries for you. Then you define the flow, and this is an array of operations that a virtual user will perform. In the above example, they are making a post request with a JSON body that contains a GraphQL query to the root GraphQL. You can also see here that I'm calling the set headers function that I discussed previously. And above is just a snapshot. You can add as many operations as you like here. In my script, I had about 5 different read queries that were going to be made by a virtual user in my test. But it's important to note also that if you wanted to, you could assign weights to the queries. So a weight allows for the probability of a scenario being picked by a new virtual user to be weighed relative to another scenario. We didn't do this, but above I've showed an example of how you would assign weights to your script. Let's say I make an assumption. My assumption is that users are twice more likely to make a request to retrieve systems than they are to query health checks that are live. I could assign a weight of 2 to the first query and then assign a weight of 1 to the other, and it's as simple as that. So once you're happy with your script and you've put both the config and the scenario section together, you're ready to go. And you can run the load test using the following command: artillery, run, and then the file path, file name of your script. Okay, so what happens after you run the script? Artillery will provide you with a summary report that contains detailed metrics that help analyze the behavior of your application when it's under load. So you have scenarios launched, and that's the number of virtual users that have launched a scenario throughout the test. You then have scenarios completed. That's the number of virtual users that have completed a scenario throughout the test. And then you've got requests completed. That's the total number of HTTP requests and response sent. And then you've got requests per second, and that's the average number of requests per second completed throughout the test. And then you have status codes. That's the HTTP status responses from each request that has been completed. And the request latency. That's how long it takes the server to receive and process a request. And it's measured in milliseconds. So that's great, we have all the metrics and we understand what they do, but how can we actually use the metrics to help identify a performance issue? So above is a real example of one of the early summary reports from our script. What we noticed was that the request latency started to degrade rapidly throughout our load test. It began with 67.6 milliseconds and then suddenly ramped up to reaching a median request latency that exceeded 30,000 milliseconds. This was really concerning as we were only sending on average about 20 requests per second, and we're expecting our application to be able to handle a much higher load. Also, out of the 6,000 scenarios launched and completed, more than 90% of requests received an HTTP status code 500, indicating that the server was aware of an error, or it was simply incapable of performing the request. Or it received 503s, indicating it couldn't even hit the server at all. So the metrics about the response times, the throughput rates, and the status codes helped us identify a serious performance issue early on in the development process, that would essentially stop our application from running. Right, so now we've got a performance issue. How do we find the culprit? So we ran several tests singling out each query and sending the metrics to Graphite and Grafana. And after a couple of attempts, we had found the culprit. It was this GraphQL query which was trying to retrieve the first 600 systems that had a bronze service tier. In fact, we were reaching 100% CPU when running this query, and it was at the very low rate of 10 requests per second. CPU is the central processing unit in the computer that does all the computational work. So the fact that we were reaching 100% CPU utilization with this very low level of requests per second led us to believe that perhaps it was an application issue. So we wanted to determine whether there was something in our code base that was causing the CPU to reach 100% utilization. And a good starting point was to generate a flame graph. A flame graph, so in order to generate a flame graph, we used to profile the CPU usage, and we used a plugin called 0x. Again, it could be installed using npm, and with a second command, it will generate the flame graph for you and open it in a separate browser. So it was really quick and friendly to use. Above is the flame graph that we generated. With a flame graph, all the data is on the screen at the same time, and the hottest code paths are immediately obvious as the widest functions. Annoyingly though, there was nothing unusual being displayed. There was no single line of code using up the whole CPU usage that we could just try to fix. So we need to think about what else could be causing this performance issue. So we looked at our database. Our database was a Neo4j instance run by GrapheneDB. So when a user made a read query using GraphQL, it hit an execution layer. In our case, it was this npm module called Neo4j GraphQL.js that translated the GraphQL query into the Cypher query. So if you take the query above that was causing the performance issue, it would get translated into this Cypher query. And then this would then send the request directly to our Neo4j instance. So we decided to look into the configuration of this npm module and see whether we could identify a performance issue there. And what we noticed was that the driver had a maximum pool size of 100 connections. And this meant that if a session tried to acquire a connection, but the pool size was at capacity, it'd have to wait until a free connection was available, or the request would time out, causing an HTTP request of 503, which we had seen in the load test. So this suggests, we could be facing the performance issue if the number of connections were exceeding the limit when running the load test. So what we did was we increased the pool size to 300 and decreased the retry timeout to 10 seconds to see if this would resolve the performance issue. But we realized we weren't even reaching the capacity of 100 connections, so increasing the pool size obviously had no impact on the performance. So we then discovered that within the npm module that the queries were not being parameterized correctly when using the driver. And this would impact the performance of the query as it wouldn't allow the caching of statements within the Cypher engine. So a query plan would not be able to be reused, hindering the performance of that particular query. So we parameterized the Cypher query, and as you can see above, again, it made no improvement in the performance of our query. So we then looked into Cypher tuning. Thankfully, with Neo4j, you're able to see how a particular query performs by prefixing it with profile. And this isn't just for Neo4j databases. It can be done in many databases, including SQL. So we ran profile on the particular query using causing the performance issue. And what we're really interested to see here is the total number of database hits from this query. And in this case, it was 14,213. And the objective here of query profiling is to find a way in which you can reduce the number of database hits required to perform the task whilst keeping the output level constant. So one way to do this, to reduce the number of database hits, is to create an index on the starting point of your query. So we created an index on service tier attribute in the hope that this would improve the performance of the query. And we ran profile again. The number of database hits did significantly reduce by 2,148. However, it didn't resolve the performance issue. In fact, it had no impact on performance. So we then looked at the configuration of our Neo4j instance. What was the size of the instance? Did we have the correct RAM size? And what were the number of cores on our server? We started by running system info in the Neo4j browser, which provided us with information about the size of our database. For example, information about the number of nodes, the number of relationships that exist in our Neo4j instance. From this, we could use the Neo4j hardware sizing calculator, and what it did was it recommended that we needed to increase the size of total RAM and increase the number of cores that we had on our server. And this obviously could explain why the CPU was maxing out. So we looked at different plans, and we also discovered that the plan we were on was on a shared resource. So we made the changes. We upgraded to Performance 1, which had 8 gigabytes of RAM, and it had 2 cores on the server. Once we made these changes, we ran the script again. And confusingly, even with a dedicated resource, the overall performance had actually got worse. So not only did we not improve it, but it had even significantly degraded. So this led us to believe that, it could be a network I/O bound issue. When database results are queued for processing by the CPU, the input-output's limited, and so maybe the queue of the results would back up, causing a struggling CPU. So that was kind of where we were heading next. So you're probably thinking, I've done all these troubleshooting techniques, but come on already, what was the actual fix? And unfortunately, from one day to the next, the performance issue just disappeared. I know. We were all of a sudden able to make 25 requests per second without our application crashing. Thankfully, we had stand-ups daily, and so my colleagues did not think I was going crazy. But for this particular example, we really weren't able to find the solution to the problem. So why have I shared this example with you? Surely I'd want to show you an example where, I significantly improved performance. But, what I learned was really invaluable, and I want to be able to share that with you. I've been able to build a personal toolbox with tools and techniques that will help me identify and eradicate future culprits. But also, there were really practical outcomes. First, we were able to measure, assess, and improve the overall performance of our application. By load testing, we were able to detect a performance issue early on, and as a result, dedicate time to help improve the performance of our application before it went into production. But we were also able to assess the reliability of our application. By load testing, we increased our confidence that our application could stay online given a certain level of traffic, and really understood at what point we would need to consider scaling our application in order for it to stay online. So to conclude, if you really want to fully understand the performance and reliability of what you're building, you should all be load testing your application. Thank you for listening, and we're also hiring, so you can visit the site. Does anyone have any questions they'd like to ask? Okay. No? Yes? Okay.
Did you at any point consider whether it would be true
No, that's a very good point.
Can you repeat the question?
So he was asking whether the tool itself could potentially be causing the performance issue, which is a completely valid question, and that is a good thing to consider, which we didn't. I think the reason we didn't go in that direction was just because we had such a low level of requests per second that it seemed quite like our initial thought was what's happening in the code that's causing it. But yes, definitely that's something we should have considered. Any other questions?
You didn't manage to re-simulate the bad performance in any way?
No.
You just manually went better and that was that?
It was terrible. Honestly, we were working on this performance issue because obviously we wanted to release to production, and we went on an away day, so the entire team was not working for that whole day, and went back, and in the morning at like 8 I ran the script and it was like perfect performance, and I went to stand up and I was like, I'm really, you know, that performance issue I've been talking about for the past 2 weeks, you know, it's gone. And they were like, oh, what was the fix? And I'm like, I really don't know. So yeah, no.
If you were at an away day, obviously it comes to mind is like whether you hit any kind of resource throttling limits of the infrastructure you were running on. So having left it alone for a day, you come back and you.
Yeah, no, that's correct. But what happened was we carried on testing it continuously to obviously capture that, but it just.
Determined to find out why.
No, I agree, and that's kind of why I like giving this talk, because people start brainstorming more ideas. It's horrible for a perfectionist not to have solved the problem. Any other questions? Nope. Okay. Thank you, everyone.
So thanks to Katie. I think Katie will be hanging around at the end.